see so many people in Durham. Well, I weren't expecting quite so many, so we've had to make some extra chairs. It's good to see everybody here. So, what I want to pick up on is, in a way, the ideas and the measurements that led us and Tom to come up with this new understanding of how the reverse intersystem crossing works. But more so, the actual consequences of that model and what you're going to expect to see in TADF molecules and what you can do with them. The main thing is, we never want to forget that at the end of the day, we are all applied scientists when we're working here. Yeah? And this is the end goal. And we do have a real end goal. When you make TVs, we're going to make molecules that have got to go into real applications. So a lot of things we talk about, we can come up with things that work at 100% efficient. They've got to work at 100% efficient for 100,000 hours. So the latest LG TVs are now on sale with a quoted 100,000 hour lifetime. So it's not just making whoopee molecules, we're going to make whoopee molecules that last. Anyway, let's start off. So hopefully now everybody's convinced that the way this reverse intersystem crossing operates is that we're going to have to get a mixing of a local triplet and the CT triplet. And that mixed state will then allow the coupling back to the CT state. So we work on that premise, then the important, as Tom said, the important gaps, the gap between the local triplet, either donor or acceptor, and the triplet CT, and the gap between the two CT states. But we've now got a process which depends on two completely different types of excited state. One's a local triplet state, and one's the CT state, which is incredibly sensitive to its environment. But only one of those states is incredibly sensitive to its environment. So we should be able to play around with these molecules and tune them in different ways to maximize or kill the reverse intersystem crossing, and therefore maximize or kill the TADF. And so some of the applications and the uses of these molecules, you're going to have to think a bit further than just understanding the molecule. So that's what I'm going to focus on. Okay, so as I said, two different types of excited state are involved. So what happens to these molecules and the physics of these molecules when you start to play around with their environment? So let's start off with one that Jonathan touched on this morning, first session. So we have our slightly twisted acceptor unit and phenanthroline donor units. Okay. It works very much like a normal DAD CT state, TADF molecule. The donors are pretty orthogonal to the acceptor. It looks like something we would draw up on paper and design. You'd never guess that's what we did. So when you look at this, the basic spectroscopy, we can see that in this particular molecule, if you look at the absorption spectrum of the acceptor and donor fragments on their own before we make the DAD molecule, then the absorption spectrum of the DAD molecule matches. But in this particular molecule, there's a new absorption which appears in the DAD molecule. Now, if you look very hard at a lot of these molecules, you can see a very small induced absorption. Jonathan touched on it, that in some molecules, the shift of this new absorption, this solvent, is a blue shift, so it looks like that state has got more predominant N-pi character. In this particular molecule, it red shifts with increase in solvent polarity, so this one's got more pi-pi star character. But these very weak states down here that appear in these molecules are probably highly mixed. And if you go and read Crystal Marion's paper, she spent probably a lifetime looking at the mixture of states and the mixture of N-pi star and pi-pi star character in these kind of compounds. If we look at the emission of this molecule, then yeah, the emission is nicely red-shifted from the emission of either the donor or the acceptor fragment. So it's a nice CT state. And again, you put it in different polarity solvents. The the emission redshifts with increasing polarity. So it's a nice CT compound, should hopefully give a strong TADF, should be able to make nice devices with it. So if we look at the time-dependent emission, and this is in MCH. So MCH, going back, is the very weakest polarity solvent or environment that we can put this in, and so we have the most blue-shifted emission. If you look very carefully, you can see that that emission has got a little bit of structure. These CT states aren't pure states either. A CT state is a combination of the locally excited donor, the locally excited acceptor, and the CT. And depending on the environment and how you stabilize the CT, that excited state could have more local character than CT character. And as you push it in polarity, you will get more and more CT character because you stabilize a charge-separated state. It's important to understand what these states are. So in MCH, we've got the weakest environment, we've got the weakest stabilization of the CT state. Then we can see that the actual TADF component, so here this kind of plateau region, at room temperature you can see it well, so we get this characteristic now decay of the prompt emission. Then we get a plateau region where you're getting decay which is almost time independent. This process coming back to the reverse into system crossing. And this process here which is temperature dependent. So this is the step which is the reverse into system crossing. And it switches off very quickly. And if I look carefully, when you get down to even 260 or 200 Kelvin, this decay in this region is actually power law. It's not exponential, it's a power law. Basically, what we think that means is that you've got a distribution of barriers. And because this is a weakly stabilized system, that distribution of barriers, and you remember you've got two barriers now that you can have distribution for, that controls the rate at which the triplets come back to the singlets, and instead of giving you exponential decay, it actually gives you more like a power law decay. So you can start to understand a bit more about how this RISC process works by looking at these plots in non-stabilized compared to stabilized states. This particular molecule took Paloma a while to understand, because not only do we get initial emission from the donor, and in fact, in a lot of these molecules, when you look at the first nanosecond, you're exciting the donor because you're hitting it with 355 nanometers or 337 nanometers. You see a little bit of the donor emission before the slow electron transfer occurs. You can actually time resolve the electron transfer in these molecules, and it's typically around 3 or 4 nanoseconds. Okay, so the electron transfer rate is the slowest electron transfer rate ever measured in these systems. But then we get the electron transfer, we get the CT state formed early times within about 15 nanoseconds, and it relaxes, but it's in a very weakly polar environment. And by about, where are we? A microsecond, then we're into the pure CT, but we haven't got a lot of CT. And in this particular molecule, when you look after about a microsecond, you can just see that this blue edge shifts a bit, sorry, the red edge shifts a bit, and we can start to see a bit of the phosphorescence coming in. And the phosphorescence in the CT is very close to these molecules, but I'll show you that you can differentiate the two. And when we do that, we look at the phosphorescence in more detail at a millisecond, and we get this CT emission. The optical gap, so that's the gap between singlet CT emission and phosphorescence, is about 160 millielectron volts. That's quite a big gap, so that's why you've got quite weak and very strongly temperature dependent delayed fluorescence. We go to toluene. The polarity difference between MCH and toluene is not very much, but for these molecules it's enormous. It's how sensitive these molecules are. Okay? So this is now again a time-resolved emission for the same molecule, just in toluene. You can see now, you can see how strong this delay component is compared to the prompt. And you can see this part here is effectively temperature independent. It's just coming back. Triplets are coming back to the singlet. Take the ratio between the prompt and the delayed, you get about a factor of 5. So the actual reversing the system crossing rate in this particular molecule in toluene is about 1/10 to the 6. So it's much faster than it was in MCH. So just that tiny change in environment, the polarity between MCH and toluene, like chalk and cheese to this molecule. Huge differences in terms of delayed fluorescence. Now, this one is really fun. It gives fantastic traces when we look at the temperature dependence of the delayed fluorescence. This is Palermo's little artwork. It's great. It's so good that we can actually pick out 2 isoemissive points as a function of temperature for the decay of the delayed fluorescence. So up here, in the first few tens of nanoseconds, this is prompt CT emission. And this is the spectral trace. So you can see what the spectra look like in these different regions. Right? The spectrum almost identical apart from very long times, and we see a grow-in on the blue edge, and that's the phosphorescence. So immediately going from MCH to toluene, we've inverted the order, energy ordering, of the CT and the triplet. So we've pushed the CT, say, below the triplet now, in this one, in changing the environment. We look at these different regions. So in region A, CT emission, and as we increase the temperature, we increase that delayed fluorescence component. So that's what you would classically call the TADF. But in this region B, we still have emission which is almost identical, but now if you look carefully, it's, this emission decreases as you heat the system up. This is the wrong way around, so this is not TADF. What it is that in this region we've got a mixture of both the CT emission and phosphorescence. Now, as you change the temperature, then the rate of reversing to system crossing goes down, but the quantum yield of phosphorescence goes up, and the rate of phosphorescence doesn't really change. So you get a more dominant phosphorescence here at lower temperature, and at high temperature you get more dominance of the TADF. So we get an inversion here because we have a mixture of phosphorescence and TADF. And then right down here we just have the phosphorescence only. So the photophysics of these systems is quite complicated because you can really start to see both the TADF and the CT and phosphorescence. And if the two states are very close in energy, then it's very hard to differentiate them in terms of their spectrum. But you can pick them out on the way in which they decay as a function of temperature. Oh yeah, and the gap, now the gap is down to, on the next one, the gap is much smaller, and the gap in toluene comes down to about 70 millielectron volts. And again, that's the optical gap. That's the difference between CT emission and phosphorescence. So you can see that we've shifted the gap between those two states by something like 100 millielectron volts, just going between toluene and MCH. So that's why now in toluene, with these states much closer in energy, then the reversing system crossing has got a much higher rate. Frank-Condon overlap is going to be stronger, everything plays in your favour, and that's why in toluene the system is a much better TADF material. Okay. Now, as Tom said, we've got two gaps in that system. You've got the gap between the local triplet and the triplet charge transfer state. You've also got the gap between the local triplet and CT1, and you can measure both of those gaps independently, I think, because if we do the thermal activation plot, and you've seen these already in Jonathan's talk and Yuhai's talk, you can measure the onset of the delayed fluorescence as a function of temperature. And you see for toluene it comes out at about 30 millielectron volts. Yeah? And the error's good. So this gap that you measure with the thermal activation is different than the optical gap. That's because we think this one is measuring the gap between CT3 and LE3, and this one, of course, is measuring the gap between CT1 and LE3. So from this, we can measure what the actual exchange energy, the gap between CT1 and CT3 is. And in this case, where we've got inversion, remember the triplet CT has got to be at best the same energy as CT1, but probably slightly below it. And so the gap between LE3 and CT3 is probably in a region of about 100 millielectron volts. You pick out these two different gaps, and they're both important. Right? They both contribute to the actual rate of reverse intersystem crossing. So the main point is that by just changing the polarity very slightly, we get a complete change in the photophysics. We get an inversion of the ordering LE3 and CT and the CT state. We then take that molecule and go to ZNX. So again, our favourite in a host. Then the polarity of ZNX is very close to MCH, very slightly higher than MCH, less than toluene. Again, we see in the films, we get very nice pure CT emission. CT dominates. We look at the decay as a function of time. Then at room temperature, then again, we get in long prompt emission and then delayed emission. So obviously the gap is a bit bigger than in toluene. And by 80 Kelvin, then you can see that you've almost quenched all of the temperature-dependent DF. Because the gap is just too big, and 80 Kelvin isn't enough to get you back with reverse intersystem crossing. And if you look at the spectra, then we can see that we start off again, but the prompt is more to the blue. We get relaxation, and by 23 nanoseconds, we've got pure CT character down here. And at 80 milliseconds, which is the green, it is just phosphorescence that's left. And the key point is where that intersection is, because that's the energy gap between the two. So in ZNX, the actual gap between fluorescence and phosphorescence, if you like, is only about 10 millielectron volts. It's very close in this system. The thermal gap still stays about 30 millielectron volts, which says that the CT exchange energy is fairly constant. It doesn't matter, because the polarity change between MCH and ZNX is not very high. This is how we can really see the phosphorescence. And as far as we can tell, the phosphorescence is independent of the environment. We can't see very much shift at all. The biggest shift that Durham has ever measured is about 10 millielectron volts, the difference between solid and solution. Right, so that's that molecule. The gap is fairly large. It makes devices which are about 14% EQE. And that's just to show you the energy levels in ZNX. So from this data, this is what really led us to understand that it was the CT and the LE states that were involved. And you could start to play around with them independently. And thus we had to have this model that incorporated both the local triplet and the CT state. So up to now, everything that people have talked about, well, from one slide from Jonathan, thank you, is looking at emissive states. But the emissive states aren't all the excited states in the system. Some of these states are dark. So we want to look at the whole population, not just the population that emits. So the way that we do that is by doing this photo-induced absorption, which I'll talk about in a second. One thing we've been desperate to do is to be able to change the polarity environment of a TADF molecule in solid state. We wanted to take out the solution effect. We wanted to have it in solid state and be able to change the polarity. And we found a system that does that. So this is the 2K molecule now. Jonathan mentioned this. This is the first molecule that we found that was very good TADF. And if you look in toluene, which is here, and methyl THF, which is down here, you see that we get a very large sort of anachromic shift, and when you shift the CT state right out to the red, then the quantum yield dies on you, which is what you'd expect, because if you stabilize the charge transfer so much, the lifetime's so long, non-radiative decay competes with radiative, and you lose all your fluorescence. But the important thing is we found if we put this molecule into polyethylene oxide, which is a polar solid, and as you cool polyethylene oxide down, the actual dielectric coefficient changes, so the polarity changes, we can see that we get a shift from, try and find out where it is, here we go, at 290 Kelvin, this is the CT emission. By the time we get to 150 Kelvin, it's shifted right back up to here. So it's gone from something like toluene, or a bit stronger than toluene, to Xeonex over 150 Kelvin. So we've got a handle on being able to tune the environment of the TADF molecule in a solid. It makes it easier to do spectroscopy. If we take just the donor unit, just phenothiazine, right, just to show you what happens, you compare the emission of the donor in toluene or methyl THF, nothing much happens. It really shows that it's the CT state which is doing everything and gives you all the subanachromic shift. It's not just some weird perverse behaviour of the donor unit or etc. So, how do you look at dark states? How do you look at the total population? So Jonathan mentioned it in passing. Basically what we do is you excite the singlet transition, you allow for natural intersystem crossing to take you over to a triplet manifold to produce you a triplet population, and then you come and do an absorption spectrum. You can either do a transient absorption spectrum in femtosecond or picosecond, or you can do quasi-CW and look at the absorption of this triplet state, so you can monitor the population of this T1 state by its absorption. And you can also look at things like you can get S1 to S2 as well. So in a lot of femtosecond measurements, you'll see a lot of this kind of transient absorption and decay, looking at these states. But we're interested in these much longer lived states. Okay? So we do quasi-CW. So the probe is a continuum white light source, not pulsed. The laser is just a normal 375 diode laser, which is electrically chopped, driven by a lock-in amplifier. And since it's chopped, you can look at two different signals. You can look at the signal that you measure, so that the induced signal in the white light, which is going with the same phase that you're electrically chopping the laser, and that's looking at processes which have a fairly short lifetime, so they keep in phase with the chopper. And you can also look at signals which are out of phase with the chopped optical beam, and those are processes which have got a lifetime longer than the rate at which you're chopping the laser, so they lag behind. So with this technique you can pick out fast-ish processes and slowish processes, but you can't tell the real lifetimes. So this is for 2K molecule. This is Mark's work. Oh, there he is, right in front of you. Okay. And what we've done is we've taken our 2K molecule and we always reference it to the donor unit on its own. So these are in Xeonex. Yeah, these are in Xeonex. Yeah. So the solid lines are just the donor unit, and the dashed lines are the DAD molecule in both cases. The black is room temperature, the grey is 20 Kelvin. So the deep platinate is room temperature, and the lighter platinate is 20 Kelvin. Platinate is the colour of Durham University, that's why we chose it. We don't call it purple, we have to have a posh thing. Right. So if we look in phase, so this is looking at processes which are kind of fast on a time scale of milliseconds, because we're chopping the laser at about 70 Hertz. So we can see in both the donor and the 2K molecule, we get a very strong induced absorption here at about 450, 460 nanometers. And since it's both in the donor unit and in the 2K molecule, and from the literature we know that this is the triplet absorption of just a donor. So this is picking out the triplet population that's kind of residing on that donor fragment. And you can see that if you look at just the donor, out here towards the red, there's very little of anything else. But in the 2K at room temperature, you get this very strong red photoinduced absorption. And we get much less triplet. So we're pretty sure that this is the CT, and this is the photoinduced absorption of the CT state. But it's not in the single donor, but it is in the 2K. And at 20 Kelvin, it's gone. So there's very little short-lived CT. At the longer times, then again we see fairly strong triplet absorption. But in the 2K molecule, we still see a bit of induced absorption with very long lifetime, which is of CT character. Though we're fairly convinced that this is actually population residing in the triplet CT state. But it's much longer lived. And the lifetime of this, I'll show you in a minute, is much longer than the emission from the CT1 state. So we're pretty convinced you can actually see a population in the triplet CT state as well in these measurements. Just to show you why we're convinced that's a CT, if you take the molecule 2K and you put it in toluene and then methyl THF, then we see that in phase, in toluene we get very strong emission measured on the photoinduced absorption spectrometer. That's a positive signal. And in methyl THF it's red shifted and it's very small. So it's just like the normal integrated fluorescence that you measure. If we look out of phase, then you see huge induced absorption in both toluene and methyl THF. So this is got to be the CT. And if you look in the literature for this donor molecule, you can see that in water it makes and you photoexcite it in water, it makes a solvated electron, which leaves a positive charge on the donor, and it has a similar kind of induced absorption. So you can identify that we're pretty sure that we can see these CT states in this photoinduced absorption. So now we go looking as a function of temperature at what happens to these dark states. Well, they're not all dark because we see a lot of emission. So this is in phase, this is looking at the short-term processes. So this is when we're actually seeing the emission of the CT1. And what you find is at room temperature, there's not very much emission. You cool it down to about 220 Kelvin, we get lots of CT emission. And you cool it down even further, and the CT emission drops again. You can see that when we get maximum CT emission, we're actually even seeing some CT state in phase. Yeah. And at the lowest 20 Kelvin is when we get the strongest triplet signal. So at 20 Kelvin, everything is just left in the triplet. It can't cross back. That's why we can see it. So you can see that we get a maximum in the photoluminescence quantum yield, and it's not at the lowest temperature. It's at 220 Kelvin. So it's not just changing the quantum yield, we're changing something else. And remember, as we cool the polyethylene oxide down, its dielectric is changing. So something's happening as a function of changing the polarity of the environment, the molecule. It's quite profound. If we look out of phase, we look at the really long time states. So we don't see any emission because we're now looking at very long lifetime processes. We see the triplet much more strongly now because obviously the triplet is much more long-lived, and you can see that again the intensity of the triplet-induced absorption is highly temperature dependent. It grows in and then dies away again a bit. And at around about 200, 220 Kelvin, we see a maximum in the absorption of this CT state. At room temperature, we don't see very much CT state, and by 20 Kelvin, it's almost all gone. So again, we see a maximum of the CT at about 200, 220 Kelvin. So if we plot the energy position of the CT state compared to the local triplet, and we're assuming that local triplet isn't changing. As far as we've measured it, it doesn't change. We see that the energy position of the CT, as we cool it down, at about 220 Kelvin, is resonant with the local triplet. Now, as you cool it down further, the CT goes the other side and goes to higher energy. So we go into resonance and out of resonance with the local triplet. At the same time, you look at the intensity of the emission you get. The maximum occurs when you're resonant between the CT state and the LE state. And then you shift away from it, and it starts to decay. And then at real low temperatures, then you're really killing the TADF, and that's why the intensity drops. So you can prove that by tuning the CT state independently of the LE, and you tune the CT state through the LE energy, when you get in resonance, when you should get the maximum RISC rate, hey presto, you get the maximum emission from the CT state. Okay. So we're pretty convinced that that's telling you that the model's right, and it's the LE coupled to the CT, which is the key to the reversing to system crossing. So as we come up with our nice little diagram, you're going to have these three different types of TADF. The good one is when you're resonant. You have to have all three states resonant with each other to maximize the RISC, because you're minimizing the gaps. You can have a state where the LE is below the CT, and that's easy to understand. You've got a thermal barrier, and that's why you've got thermally dependent TADF. But of course, you can push the CT states below the LE. We've seen it already in the first molecule. And then potentially, the coupling again is still thermally activated, but you've got to couple the population which is in the triplet CT, couple it up to the population that's in the 3 LE state to get reversing to system crossing. But then it doesn't really matter, as Tom showed. As long as the gaps aren't too big, it doesn't matter which way round you are. This, it actually looks like this. It's a mirror image. But this is best. Okay. And we've seen now that you can tune this, because I can tune these and leave these the same. So, what happens when we go to a device? How can we use that? What's the consequence of it? So this is another one of Jonathan and Martin's little friendly DAD molecules. Still got the twisted acceptor, but we now have a twisted donor. That pushes the triplet energy of the donor up. This twist pushes the triplet energy of the acceptor up, and the CT state's a bit higher. So this is the blue emitter, blue TADF emitter. We do the measurements of the CT emission and the phosphorescence and the time decay. You can see, yep, it's classic. We get prompt CT decay. We get the DF part, which is strongly temperature dependent, and then we get a bit of phosphorescence at the end. So it's a classic DAD TADF molecule. But since we get such strong thermal activation, it says that we've got a large gap between one of the LE CT states. And in fact, when we do the measurements, then the gap here is about 150 millielectron volts. So it's quite a large gap. We don't expect to get so much TADF. Okay. So this is the fluorescence and phosphorescence. So you can see this gap quite nicely at 80 Kelvin. At room temperature, you can see even down to a millisecond, we're still getting predominantly CT emission. So a gap of 160, 150 millielectron volts is still small enough to give you quite efficient TADF, but it's slow, which is not going to be fantastic for devices. But that was done in ZNX. When we were making devices, one of the choices for the host material that we could use is a polar host called DPEPO. I haven't got the structure for it, but it's got a bit of polarity. It's not as non-polar as ZNX. So if we compare the decay of the emission of this molecule in DPEPO compared to ZNX, you can see that the DF switches on much faster. and almost all of the emission comes out pretty quickly, and it's all DF, and the temperature dependence is much weaker. So even at 80 Kelvin, we get a strong DF component. So it's immediately telling us that the gap here is much smaller, and the rate of RISC is much faster. If we look at the emission, so this is from the device, just to show you how it compares in terms of phosphorescence and electroluminescence. If you look at the onset of both the EL and the phosphorescence, and if you overlay the fluorescence on top of the CT, the gap here is tiny. Right? We reckon it's around 5 millielectron volts. So the polarity of the DPEPO has shifted the CT down just enough to make it isoenergetic with the triplet state. Okay? So this should be really good TADF material. Okay? So we can see from the temperature dependent measurements that we get almost all of the triplets come back with TADF. When you make the device, then yeah, it's pretty bright. We get a very nice low voltage turn on, and we don't get much roll off. But the best thing of all, the EQ is 22.4%. So by using the host to tune the gap to give you the most efficient TADF, then you get fantastic devices. Right? And this is in the blue. And this is quite deep blue as well. So I think this really confirms the fact that what you're trying to do is minimize the gap between the local triplet of either the donor or the acceptor, it doesn't matter which one, it will couple to either, and the CT states, and you want all three CT states, sorry, both CT states to be the same energy, minimum electron exchange. That's why it's got to be perpendicular. So you've still got to minimize the electron exchange in the CT states. You still have to have that, because if you don't do that, then CT3 is going to be much below CT1, and one of your gaps is going to kill you. So you still have to minimize the electron exchange in the CT manifold. You've got to have the triplet state close to it to couple to allow you to have this reversing system mechanism. Okay? And then it works. So we're not the only ones that have got devices at this kind of efficiency. But it does show you that now you are up there with phosphorescence. And it's deep blue. Don't ask us what the lifetime is, because we go very light. We leave that to our sponsors. They never know where the hiding is over there.
You can see the lifetime in your graph.
It lasts long enough to do the measurement.
Exactly.
What do you do to it on the third data point to sort of boost its efficiency?
We don't know, but it's repeatable. Yeah? It's always repeatable. And if you change thicknesses and things like that, it's still there. You have no idea what it is, but it's always there. So that's another little quirk of TADF that someone's going to have to go and find out. So I think that just summarises what I've already said. I think we're getting an understanding now of what's happening. Tom's model is showing you how you get reverse intersystem crossing in systems that otherwise would have very little spin-orbit coupling. It's a second-order mechanism. So we can come up with these design rules to tell you how you're going to get very efficient with TADF. But as you see from that device, you have to be careful what you put your TADF molecule in. You don't have to change that gap by very much at all, and you will completely kill the TADF rate, and therefore the device will be lousy because the states are living in the triplet so long that get quenched by the polarizer. Okay? So it's a system now, not a molecule, it's a system. You've got to think how you're going to use that molecule in its system, in its device, to get the best out of these molecules. So I think it shows you can maximise the RISC. Quite large here. But how you do it is quite complicated. I think you've seen from Jonathan's this morning, if you try and do things that you think, oh, this is going to make a perfect molecule, they bite you, they don't work. We make them completely rigid and can't twist, and hey presto, we got rubbish. Well, we got some quite interesting things, but it wasn't what we wanted. Yeah. And you have to be careful where you put them in. So with that, thank you very much.